Hello everyone. In this video, our question is to push or to pull. To push or to pull. And the thing I'm thinking about of what to push or to pull is furniture. Okay, heavy furniture. And this related to me recently, right before the social distancing. My wife wanted to kind of rearrange some things in her office at work, get some new furniture in there. So we spent a solid day moving stuff around there, and some of that stuff was really heavy, like bookcases, and her desk was the heaviest thing. It was a big L-shaped desk with made of a lot of metal, so it was really heavy. And we had to get that moved around, and for a lot of the furniture, I had to really think about what the best way to do this would be. And one of the things I had to decide is whether to push or to pull. Now, some things you don't have much choice. Like if something's taller than me, like a bookshelf is taller than me, it's really hard to pull on the bookshelf when it's that tall. I didn't really want it to tip over and fall over on me, so I tended to push those out of safety. However, things that are shorter than me, like her office desk was shorter than me, I had the option. I could either push it from behind or I can pull it across the room, and I would slide it across the floor. All of these things were too heavy to pick up. Okay, even with two of us there, it was too heavy to just pick up off the ground. So we did have to slide them across the floor, which means there is friction there. And believe it or not, whether you push a desk across the room or pull the desk across the room, that's going to make a big difference on the amount of friction that I have to face. Okay, so like this table behind me, it's not that heavy actually, but if I need to move it, the question is, do I push it like this? Okay, just try to push it across. I'm not going to, because I don't actually need to do that. Or I can come on the other side here. All right, and then I can try to pull it. Okay, oh, I moved it a little. I want to fix that. All right, so that's the question. But we're talking about like even heavier things, really heavy things. Okay, so to analyze that, first of all, here's a system diagram. Okay, a system diagram. Remember, a system diagram is like an actual picture of what's going on. So on the left is a person pushing an object across the floor, whereas on the right, the person is pulling. And what I want you to pay careful attention to is the angle of the applied force. The angle of the applied force. So this person who's pushing on the box, notice how the arms are not perfectly horizontal. They are slightly downwards. Okay, slightly angled downwards. And over here on the other side, the person pulling on the box, the arms are angled upwards. All right, so the applied force is not horizontal this time, and that's mainly what's going to be different in this lesson compared to the previous lessons. In previous lessons, everything we did was either horizontal or vertical, kept it simple that way. We're going to end off the topic and end off the unit actually with some problems that involve angles now. All right, so to compare the two, I'm going to draw free body diagrams. So on the left, the person pushing, and on the right, the person pulling. So I'm going to start off simple. There's something that's the exact same, or that's going to be the exact same in both free body diagrams. And that's going to be the force of gravity. And the force of gravity is going to equal to m times g. No matter whether you push the object or pull the object, the mass stays the same, and the value of g is 9.8. So that's the exact same in both free body diagrams. The next thing I'm going to compare are the applied forces. So remember, the person pushing the object that's shorter than the person ends up applying a force that's angled down. I call that below the horizontal. Okay, so this applied force is aimed below the horizontal, whereas the person pulling it, who's taller than the object, when they're pulling, their arms are angled above the horizontal. Otherwise, I drew them the same size. Okay, I'll assume that the person can apply the same amount of force whether they're pushing or pulling. It's just the direction of the force is going to be different. Now, you may want to think back to when we did work with vectors at angles, maybe in projectile motion or even earlier in this unit. When you do have vectors at an angle, it's often useful to break them down into perpendicular components. So for each of these applied forces, I've broken them down into a vertical component and a horizontal component. A horizontal component and a vertical component. The two horizontal components are the exact same. Okay, they both point to the right and they're both the same size. The vertical components are the same size, but the one on the left, it's aiming downwards, whereas the free body diagram on the right, it's aiming upwards. Okay, otherwise, everything else is the same. And that is going to end up making a big difference to our problem here of whether we should push or we should pull. Okay, and that's because of the normal force. So I'm going to do this one diagram at a time. On the left-hand diagram, look how long I drew the normal force. I drew it longer than the force of gravity. And that's because the object is not moving up or down. Okay, the object is getting pushed across the floor. So vertically, everything should be balanced vertically. So if I look at what I have going downwards, I have gravity going downwards, but I also have part of the applied force going downwards. Okay, I've got two vectors pointing down. So I have to draw an upwards arrow that balances both of them. That's why this normal force has to be so long. It's equal to mg, the magnitude of the force of gravity, plus the magnitude of the y component of the applied force. Okay, so it's a large normal. But what about on the right-hand side? Well, on the right-hand side, I can draw my normal a lot smaller. And why is that? Well, again, the vertical forces have to be balanced. The object is not moving up or down. So I've got gravity going down, but this time the applied force is somewhat upwards. This y component of the applied force is pointing upwards. And that's going to neutralize a little bit of the gravity already. Okay, that's already going to partially cancel out the gravity, which means my normal force only has to cancel out what's left over, which is not as much. Okay, the magnitude of that's going to be mg, the magnitude of the force of gravity, minus the magnitude of the y component of the applied force. So because of the angle of the applied force, the normal force is going to be affected. So when you pull, the normal force is less than when you push. Okay, this normal force is less than that normal force when we compare the two situations. And as we know, the formula for friction is mu times normal. The amount of friction is mu times normal. So if the normal force is smaller, then the friction is going to be smaller. Okay, so there's the last vector there. This friction is going to be small because it's going to be mu times normal, and normal is small. whereas on the other side, normal is large. So mu times normal is going to be larger. And look how I drew how long this friction is. I kind of drew it so that it's hard to tell whether or not this box is even going to move, because you have this applied force going to the right. You got this friction going to the left. Is the applied force bigger than the friction? I mean, it's hard to tell. However, for this one, since the friction is so small, the applied force is definitely big enough to overcome that friction and get that moving. Okay, so when I'm moving furniture around, anytime I have the option, I'm always looking to pull with the force angled slightly upwards. Okay, and because by pulling angled slightly upwards, I make my normal force smaller, and that makes the friction smaller. So that should make it easier to move. It should also make it less risky to scratch the floor, because the normal force is kind of a measure of how much pressure the floor is pushing against a piece of furniture. So if it's a smaller pressure there, there's probably a less chance for it to get scratched. All right, so that's this video was conceptually showing the difference between an applied force going below the horizontal and applied force going above the horizontal, and how that affects the normal force, which in turn affects the friction. And we're going to apply some actual numbers. In the next video, I have a problem where I use actual numbers. That video is going to show a problem where you push an object, and then I'm going to get you to practice one where you pull an object. All right, I'll talk about that more in the next video.